Okay, hello everyone. My name is Hyun-Sung Lee, and I'm going to introduce about open source on-device AI software platform of Samsung. So in this presentation, I will introduce four open source projects, which is NNStreamer, NNTrainer, and One, and device MLOps. So let's get started. So what is on-device AI anyway? The main difference between the traditional cloud-based AI and on-device AI is the place of the neural network model is located and executed. Traditional cloud-based AI requires the models to be under server. So computation is run under server. Therefore, the user data should be transferred from the device to the cloud. On the other hand, on-device AI system keeps the model, which is trained and deployed by the cloud infrastructure, at each device. Therefore, computation and user data is kept on device. Then, why do we need the on-device AI while we already have a traditional cloud-based AI? Here goes four major advantages. And the most important advantage is data privacy. With cloud-based AI, user data are sent to the cloud. And I'm pretty sure that no one likes to send their private data to the server. Another advantage is network overhead. If the user send data is audio or text, it will be okay. However, if you send the video stream, the network overhead may be excessive. And besides, on-device AI even works when you don't have a network connection. Cloud operation cost matters too. On-device AI reduces the cloud operation cost dramatically. And also, it reduces the energy consumption and carbon footprint significantly. However, there are a few challenges of on-device AI. The most significant challenge is limited computing resources. And it makes it hard to run the neural network model on device. The other challenge is hardware diversity. There are various types of devices with different hardware environments. So you need to cover such a diverse hardware environment to deploy the on-device AI successfully. So here goes the first project to be introduced, NNStreamer. NNStreamer is already deployed to many other to the companies other than Samsung. So in here, I will introduce a few services of such companies. Finders AI provides the automated retail solution for the cashless convenience store with the video and sensor data stream via the NNStreamer. Print Yanni AI performs the object detection to observe how 3D printing goes in a printing farm. iCloud AI provides real-time on-device AI solution for cameras. All these solutions are made by using NNStreamer. NNStreamer is a GStreamer-based pipeline framework for neural network. For those who are not familiar with the GStreamer, GStreamer is an open source project to process the multimedia data and televisions and broadcasting systems and multimedia applications use GStreamer. By extending the GStreamer, NNStreamer reuses the multimedia filter for the AI applications. So you can process the live stream data with higher efficiency. One great aspect of NNStreamer is it is really easy for the developer to use the NNStreamer. To use the application, one great aspect of the NNStreamer is it's really easy for the developer to make a complex AI applications. So you can reduce time to market. It allows to writing an application with a pipe and filter architecture and easily reusing the various filters. NNStreamer supports a lot of framework and hardware accelerators, including TensorFlow, Caffe, PyTorch, NNTrainer, which I will explain in later, OpenVINO, maybe Vivante, Samsung's APU, and HTPU, etc. So here's an example on how to make an application using the NNStreamer. Let's say we want to make an application to help the worker of manufacturing plants. A worker will wear a helmet with cameras on it and connect it to the wearable device, connect it to the mobile phone and the wearable device. So total process will be as follows. First, the camera on the helmet will send the video stream data to the mobile phone. Then the object detection model on the mobile phone will detect the operation of the worker. When detect the operation, then it sends the related information to the wearable device. Then wearable device will send an audio data and the IMU sensor data to the mobile phone. Another models on the mobile phone will then decide whether the last operation appropriate or not based on the gathered data. So let's imagine we're going to make an application without the NNStreamer. Then how many lines of code are needed and how much time will be consumed? First, you need to process the different types of multimedia data, and you need to run the models. We have to manage the communication process of devices. Surprisingly, with NNStreamer, you only need 20 to 30 lines of code. Because every filter on this diagram is already implemented. So what you have to do is just construct a pipeline and name the filter you want to use. So that's all. That's all what you have to do. So as you can see in this example, you can easily make an application using the NNStreamer. In the previous example, I already explained about the among-device AI. On-device AI will have its own models on every devices, but unfortunately, not every devices are adequate to run the models. So in this case, the low-end device will request model inference to the nearby user's high-end device. For instance, in the previous example, wearable device offloads the model inference to the mobile phone. With an instrument edge, you can easily implement among device AI. Now, I will introduce about the NN trainer. So, before explaining about the NN trainer, let's see what we can do with the NN trainer. I will show you a demonstration, and in this demonstration, NN trainer will personalize the text-to-speech model to generate a speech with user's own voice. A user will record a voice with predefined 18 sentences, and NN trainer will personalize the text-to-speech model with the user data. Please check how much time it takes to train the models, and please aware that this demonstration is recorded in Korean. So let's see. User will maybe speak and record the voice. And you can see that the training the model is start about 56 or 57. So as you can see in these examples, an trainer can personalize the model by retraining the models with the user's data. And in this case, it took about 10 minutes to train the model. So NN trainer, NN trainer is a lightweight training framework for on-device AI personalization. So the most significant challenges when you train the models in the device is the memory consumption. So NN trainer mainly focuses to reduce the peak memory consumption. And NN trainer supports various layers from the fully connected layers to the transformer layers. And if the NN trainer does not support the layer you want, you can make custom layers. And if the model is too big to train the whole network, you can freeze some of the layers, and you can train only the part of the layers. If you're not interested in training the backbone layers, you can use your TensorFlow models or TF-Lite models as a backbone. Then, why do we need to personalize the models? Let's say there is an object detection model of robot vacuum cleaner. This model is trained and deployed from the cloud infrastructure. Then will this model work for every user in every case? This is not the real case, but let's say there's a rabbit-shaped chair in my house. The base model might misclassify the chair as a rabbit. And because the robot vacuum cleaner thinks it as a rabbit, it may slowly approach it and touch the rabbit to let the rabbit move out. But this is not what I would like. So in this case, we have to personalize the models with the user's data using the NN trainer. Then let's see how we can reduce the peak memory consumption. NN trainer first compiles the graph before it trains the models. With this process, NN trainer knows when each tensor will be used and reschedules when to be used. Without the information, NN trainer have to allocate the buffer for every tensor all the time, as most other frameworks do. But with the information that the green tensor will not be used after T3, we can reuse the green tensor buffer with yellow tensor. So with only such a buffer reusing and rescheduling, we can use only 1/4 or 1/5 of memory compared to other conventional frameworks without sacrificing any performance. Then, can we optimize more? We know that the blue tensor will not be used between the T1 to T5. So we can swap out the blue tensor data from the main memory to the disk at T1. And then we can swap in the blue tensor data from the disk to the main memory at T5. But actually, there is one more thing we can optimize. Because NN trainer exactly knows when blue tensor will be used. So load the blue tensor data sometime before T5, not at T5. And we name this technique, combined with the instant swapping out, as a proactive swap. And thanks to the proactive swap, we can reduce the peak memory consumption of the transformer models from the 4 to 5 gigabytes to about 200 megabytes. And please note that proactive swap is still work in progress for the optimization. Generative AI models is the hot topic of this year. But generative AI models are getting bigger and bigger. But as I explained, we can train or infer the large model by using the NN trainer's proactive swap and memory scheduling. We have experimented inferencing the generative AI models with the NN trainer, and the proactive swap is especially efficient when inferenced with the big models. And this is mainly because in inference, the model data is read-only and swapping out is not needed. And I would like to introduce about the one project. One stands for on-device neural engine. And the main purpose of the one project is to accelerate the inference, accelerate the inference on the device. So one supports the various hardware processor like CPU and GPU and NPU. And it also supports the heterogeneous backend. So you can do something like this. So you can do the addition operation with the CPU, and you can do the convolution operation with the OpenCL. Because convolution operation is relatively complex operation, so it is more efficient to do this operation with the GPU rather than CPU. And if the hardware processor supports the fused operation, one will merge the multiple operation to a single operation. On the other hand, if the hardware processor does not support the original operation, one will decompose the original operation to a multiple operation. And one can quantize the model weight to compress the model size. So I will introduce about the device MLOps. So some of you in here may already know about the MLOps. With MLOps, the developer will collect and pre-process and analyze the data. With this data, the developer will train their models and continuously integrate and continuously and deploy the models. After the deployment, a developer will monitor its services to gather the feedback. Then, what is device MLOps, and why do we need device MLOps? On device AI, there's a multiple application on the device. So each application will have its own model and its own data. But instead of each application manages its data and the model, device MLOps will manage the model repository and data repository. And since there are multiple applications in the device, so there might be a chance that the multiple application wants to train their models simultaneously. So in this case, device MLOps will schedule the training process, and during the process, if the device is getting overheated or the battery level is low, device MLOps will pause or stop the training process. Besides, offloading, which is I've already explained with the among device AI, can be managed by the device MLOps. So this is the overview of the device MLOps. Device MLOps will continuously interact with the MLOps. So it gets the model deployed from the cloud infrastructure and push the data to the infrastructure, to the cloud infrastructure. And device MLOps will manage the training or inference service instances. And also, device MLOps will manage the inter-pipeline connections to support the offloading, which is I have already explained in among device AI. So thank you for listening to this session. I hope you enjoyed this session. Thank you.